Another draft physics presentation. So kind of an overview video, just a kind of off the top of my head description. Tyler Johnson, who's been making some comments lately, did a couple of videos, so I'll leave a link below to his channel. And his paraphrase of what I was saying in my videos is so bad that I'm saying, gee, somehow I'm not conveying this well enough. So I just thought I would do a simple version, more simple, to see if that helps any, just to resolve any confusion about what I'm saying. So anyway, so let's start with nothing. Okay, nothing. The universe is nothing. Let's just take everything out of the universe and we just got the empty space thing. Alright, and that's what I'm going to propose here. There is such a thing as nothing. There's places in the universe where nothing is happening. There's empty space and it's purely empty. Nothing. Nothing. Not ether or not something. Nothing. Absolutely nothing. Alright, and then there's other places where there's a something. Okay, and so we have two kinds of somethings. Alright, so we have force somethings. Alright, and then we have matter somethings. Okay, and they're not the same thing. See, it's a line, make even a chart here. So there's force somethings and then there's matter somethings. Alright, and the force something and the matter somethings do have two varieties. Now, I know, okay, two varieties, what does that mean? It means they have a feature. Something about them's different. One has a round antenna sticking out of it, or one has a square antenna. It just doesn't matter what you think. The two, one's round, one's a triangle. One's a square, one's a triangle. They have a distinction, and the distinction is something they understand. We don't have to understand it, they understand it. Now, it could just be polarization. It could be they fly through space one way and the other ones fly through space the other way. It's something simple like that. But let's not confuse things if we can avoid it. Alright. Now, so they could be any shape. They could be little square things, they could be round things, they could be little sparkles of energy, if that's what you want to think about them as. You want to think about them as little purple sparkly things, go ahead. I don't really care about that part. Okay, the little force bits and little matter bits. So there's empty space, and then there's these things in the empty space. Alright, now the force bits are much smaller than the matter bits. Can't really draw the difference, huge difference in really size, okay? So let's just get that figured out, that these matter bit things are big, these force bit things are really small. Now, the force bit things constantly move in a direction. They just never stop moving. They're always moving somewhere. They're always heading somewhere. And they always head in that direction at the speed of light. And theoretically, if we just forget about the matter bits, let's take all the matter out of the universe. All the planets, all the galaxies, all the heavy bits. And then we take all the atoms. If you've heard of atoms, let's take all the atoms out. And you just have these little force bits. That's all they would be doing, is flying through space, alright, in directions. And theoretically, if they hit each other, and they were all one color, you wouldn't be able to tell, because basically two things come in and two things will leave exactly the same way. You can't see the difference between them actually hitting each other and then missing each other. So, I mean, it's sort of an important thing to understand. I don't know how hard to emphasize it. But if everything was the same color, if they hit each other and miss each other, you couldn't tell. It'd be impossible to tell the difference. It's exactly the same universe will be the byproduct of them crashing into each other and bending, or going right through each other, or missing each other. Any one of those varieties of event would look exactly the same. You wouldn't be able to tell the difference. So a universe with just these things moving around, just black bits, nothing. Now the trick is, the black bits in this real universe are probably running on black squares, so to speak, and the red bits are running on red squares, so to speak, red lines, and they can't really hit each other. So now if you could make a black bit hit a red bit, you can sort of understand that now you could see the difference in the universe, because now you can tell the difference because the red bit would turn. And so you'd see the difference between the red bit going straight through or the red bit turning. You know, hey, it couldn't have missed each other because it turned. So it's now the universe has change in it. So the idea is, so understand, in the universe the red bits and the black bits are flying on different tracks. Okay, different layers of the, I can't draw it in 3 dimensions, but it's like there's a black track and the red track, and they don't hit each other. I mean, here's the red track. And you can't, the two can't cross over and meet each other, so they can never hit each other. They can only go below each other or this way, or, you know, they can't hit each other because they're on a different plane of the universe. And the catch is that the matter bit allows the black bits and the red bits to hit each other. So when a black force bit hits a matter bit, then it can interact, okay, if this was a force, the little force bits can hit inside of the matter bit, as an example, as an analogy, and they can do this go the different direction thing. They can change their direction, essentially. So the matter bits allow the force bits to do something they can't do without the matter bits. But just remember, if all we had was the force bits, then the black pieces just keep going black places, and they might hit each other, but you wouldn't know it. The red bits keep flying around, but they might hit each other, but you'd never know it. Can't tell the difference. So who cares whether they hit each other or not? Can't tell the difference. But because of these matter bits, you can tell the difference. Alright, so these bits, these little force bits moving the speed of light, are everything you've heard of in terms of their gravity and their magnetism, and they're the strong nuclear force. So they're the things holding everything together, in the sense that they're all the things that are like the invisible forces. Everything they call like a force field. Every time they talk about a field of energy or a field of something or a wave of something, they're sort of talking about these little bits. Now obviously when they're talking about water waves, that's talking about atoms, and that's a little more complicated. So we're just trying to stay with the simple functions, and we'll get to atoms in a minute. But understand that force bits are anything that you see happen where you don't see what's causing it. Like when you feel heat, some of that is these little force bits. Now some of it's atoms banging into you, but some of it is this infrared radiation, a form of light that's shining on you just like regular light, and you can feel it. It warms your skin. Alright, now so all of the things, all the light, all the energy you've ever heard of, most of it, microwaves, you know, in the oven, they're these little force bits. You know, like I said, magnets flying into each other, flying apart. These little force bits are making that happen because they're creating pressure by surrounding everything in the universe. So everything material in the universe is being hit all the time by a ton of this stuff. So just like you know your cell phone works because there's a bunch of radiation flying around you all the time. Cell phone, you know, radiation. Real photons, you can't see them with your eye, but they're just like photons, and they're flying around, and they're bouncing right through you, bouncing off of you, doing all kinds of stuff all around you all the time. And that's why your cell phone can pick up conversations, is because those signals at specific frequencies, specific timing periods of the signal coming, the little bits hitting, and it's like a little Morse code, hits the antenna on your phone, and your phone sends out your voice signal. The tower picks up the little dots, and that's how the conversation takes place. And that's how all the information is transmitted. So there's a ton of this information, you can tell, right? You can just figure it out yourself. You can say, gee, Wi-Fi, you know, it's like microwaves flying around your room all the time from your router. You know, wherever you go, you can pick it up because there's a ton of this stuff. If you could see it, it would brighten and light up the whole room if it was visible. You'd see how bright it was inside your house. It's really bright. If you've seen infrared photography, that's picking up these photons, these little bits that are coming off of everything that has heat, and it's these little radio. They're like radio waves. They're like microwaves. They're like light beams. Same thing. They're just at a different frequency, and so we can't see them with our eye, but they're in the room right now, and we're causing the atoms, the atmosphere around us, the thick atmosphere is being heated by our body, and that atmosphere, once being heated, gives off this radiation. And so that's why the pictures are fuzzy and not very detailed, is because where exactly the radiation gets produced from changes, because what's hot isn't just us, but the atoms all around us are hot. We heat them. And so they start radiating some of these signals. Okay? And all the signals are these little bits coming at a frequency. So it's just the distance between the little bits. And that's all it is. And so when you have and the bits are always moving the speed of light. They never move any other speed. One speed only. No other speed. And so when you so when you have like a very low frequency radio wave, 2,000 kilohertz, it's hertz actually, I think still works. Anyway, they're so far apart that they could be miles apart before a group of these little bits gets shot out from something, but they're in a little clump of them. That's what radio waves are producing. And most light sources are producing the same thing. There's always more than one little photon. For you to see something, you need more than one to hit you, in most cases. But when it's so, radio waves are really far apart, and then light waves are really close. They're really tightly frequencied, so they're coming in groups that aren't very far away from each other in terms of distance, timing. So lots of them at once. That's why the radiation gets more intense. An X-ray, they're really, really, really close to each other in X-rays. So that you can think of it as you get a whole bunch of them in a very small amount of distance or time. A whole bunch of them could be produced or hit you because of how close they are to each other. But everything is in that form. Most of the radiation in the universe is in this form of just these little bits coming at a frequency. And a subtle trick is that they're all the black bits, because the black bits are the electron bits. But anyway, let's go back to now the matter bits for a little bit. And let's understand. So you have all of this force bit. And now all we're trying to figure out is how does these force bits, the only way there's change in the universe essentially is that the matter bits have to change the direction by allowing the red bits to interact with the black bits and cause directional changes. And if you create directional changes, you can create streams of intensity and frequency. So you can change the frequency and how much of something is going somewhere. And some other point I wanted to make. Well, can't think of it at this second. But anyway, so the force bits can't really do anything on their own. They won't create anything terribly complicated. They can't make any of these turns. They can't do anything. They can't mix the two forms. But the key thing they're going to do eventually is this idea that you can sort of understand that if they turn 4 times, that becomes a circle. 4 turns, and you're back where you started from. And that idea of a circle is what captures energy. And that's what these matter bits allow to have happen, where a bunch of these force bits can get trapped inside of matter And then you can have the idea that inside the atom you have a whole bunch of these little bits moving the speed of light, all trapped in little cul-de-sacs going around and around and around and around. And then you take a special circumstance where you start breaking the atoms apart with a chain reaction, and all of those little things going the speed of light will be released all at once in a nuclear bomb, for example. And tremendous amount of energy trapped inside these atoms. So let's go back to the matter bits, and they're not themselves atoms, they're the things that make an atom. So if you took, so the black one I'm going to say is the electron, and we'll say the red one is the proton. And these are the elements of atoms. Now you've heard a lot about all kinds of positrons and other kinds of little exotic particles. And the thing you should understand about all those exotic particles is they're not durable like these particles are. No one's really ever blown up a photon, one of these force bits. Nobody's ever broken one of those into pieces. And there's very little evidence that they've ever really broken an electron or a proton into pieces. What they've done is thrown protons or thrown electrons at very high speed into whole atoms to see if they can create some little pieces that break off. So that's what they do in these atom smashers, is the Hadron Collider, is they accelerate these little bits, these little pieces of matter, really fast, and smash them into bigger clumps of matter, atoms, and they see what little pieces fly off, and the little pieces don't last very long. They disintegrate in milliseconds. They end up being collected by other bits of matter because they can't be maintained in this broken state. But there's no guarantee that they're not really just looking at electrons and protons that are spinning really funny. That they've been hit really hard and they're falling apart and they're spinning off in little weird directions. And so they watch these little weird things that happen, these little swirly lines, and they say, well, let's call that a positron, and let's call this a strange quark, and so they give the things strange names, but they really can't see any of this stuff. So again, if you want to believe that there are all these hundreds of little funky particles, it's okay with me. I'm just saying that you have to understand that they really don't have a great deal of evidence that any of that crap is essential to the function of matter. They can't see it. You can't, to see traditionally, you have to take these little force bits, the little tiny force items, and you have to try to throw them at something and then see them reflect off, and then you can get an image of the thing. But they can't do that with these little tiny particles because they're as small as the little force bits. So you can sort of understand you can't really throw force bits at force bits to see them, because they're not going to reflect like you throw a tennis ball at a tennis ball. What's going to happen? One of the tennis balls is going to move, and the other tennis ball is going to bounce off kind of funky. You're not going to get anything in terms of resolution. You're not going to be able to see where the tennis ball was because nothing's going to bounce off of it evenly or in any way that you could use as evidence of where something was or what it was doing. It's going to be very low in information value. Alright, so anyway, back to the story. So, can't emphasize enough, again, the force bits have a unique function. They do one thing. They don't really combine. They don't do any kind of stuff. They just get trapped. They get forced they move in a straight line until they hit one of these these elemental bits of atoms. And when they hit one of these elemental bits, there's a couple of choices about what happens and how they move. And so the idea is that for the proton and the electron, they just have inverse rules. So when a black bit hits an electron, it reflects off and gives the electron a boost in a direction. Now, when a black bit hits the proton, it doesn't give it a boost. It instead gets deflected, and it ends up turning one of these directions. It could go that way, it could go this way, it could go into the, out this way. It can go any one of those four directions and all of the subdivisions of them. It leaves perpendicularly. And the same happens when a red bit hits the proton. It just does the reflection thing, and the same rule applies to the proton and the electron. Is the red bit hits it, it will be diverted, come out in one of the perpendicular directions. So you have the idea of the right turn, which is essential to all the mathematics for magnetism and is the core of the entire function of the force as it interacts with these bits. So because of this difference in action, these essentially become the monopoles of magnetism. These things are the elements of charge. You've probably heard the word charge. Well, the fact is these things have an effect that essentially means, they've called them plus and minus. Doesn't really matter what distinction you give them, but that they have this opposite character. And this is why their character is opposite, is because they interact with the two elements of force in very different ways. So the key thing is now the structure of them, how they're arranged in atoms sort of dictates how they function. So the basic theory is that the atom has a nucleus in it. So when you hear about what an atom is, you hear that it has this inside part where the protons are, and there's something else in there called the neutrons. Now the neutrons are like electrons and protons combined. So they're bigger than a proton, but I've drawn them smaller here. But they're basically what allows the protons to get so close to each other inside the neutron, inside the nucleus of the atom, is the fact that if you do put an electron and a proton next to each other, in arrangement to each other, you could sort of understand that because of this rule about how the force leaves, that all the black force, like the force that would reflect off an electron, is just going to leave if it gets caught in between the proton and the electron, and none of the red force can get in because it's reflecting off the surface of everything. And if any red force goes into the electron and comes out sideways, well, it'll reflect, but then it'll go right back into the electron and leave again. So only a very tiny amount of force can be maintained here. Now if I had two electrons next to each other, you could understand that if they always reflect, they just keep reflecting back and forth, back and forth, back and forth, and they'd create a high, you have to understand, the closer they get, the higher the bounce rate. And the higher the bounce rate, essentially the stronger the force, the more impacts. And impacts are dictating force. That's causing motion, or a need to move. So moving the electrons closer together makes them repel stronger and stronger, just like a magnet. So this is clearly understood as this is how magnets work, is creating this reflecting force. And so inside the nucleus, what's holding it together is the fact that there's no reflecting force here or here, so these protons can get very close to each other. Now if the two protons didn't have an electron between them, you could understand that the force would just keep bouncing back and forth between them, and as they got closer together, the repulsion would get stronger and stronger. So it wouldn't be possible to get them close together without an intense amount of energy or forces pushing them together. You have to have a lot of force bits hitting them to push them together because of all of these reflections happening between them. Alright, so now on to the atom. I guess I'll have to use a new piece of paper, but maybe we'll come back to this for the summary, I suppose. Alright, so inside the atom you have the protons and the neutrons, the stuff in here, so it's all protons and neutrons. And the neutrons again are just a proton with just that little electron on it, and that makes it possible, okay, because of that little electron, for the protons to get very close to each other, for the protons to get close. So that's the inside of the atom, and the outside of the atom is thought to be just electrons in orbitals. Now, I don't think they orbit. It's probably not important whether they do or they don't, but what's really important to this discussion, to me, is understanding that the pressure between the electrons is this reflecting force. So they have energy between them that is keeping them from getting close to each other, and then they want to get close to the protons. So they're being pulled towards the protons because there's low force between this way. There's no reflecting force bouncing back and forth between the proton and the electron. So there's low pressure here. The external world is bombarding the electron from the outside, and nothing's bombarding it from the inside, so it tends to want to move towards the protons. But the repulsion between these electrons fights that movement, and so it's a stalemate essentially. And so that's what creates atoms. And the different orbitals are just diagramming the different amounts of pressure that can be created, that can tie different geometries you can use that balance the pressure between the electrons. So you can have inner rings and then outer rings. They'll call them rings, but I don't think they need to be called a ring. But anyway, so they have basically 4 or 5 of these ideas of you can go a certain distance out and you still have enough attraction to the center and just enough repulsion to keep everything in positions. And so everything's sort of in a position. Now, all the positions everything's locked in they're in very tight tension, and there's variances, little degrees of change that are happening all the time. So all of these things are vibrating in their position. They're not just in one position, but they're vibrating. So they're moving a little bit. They're shuddering. Okay, they're going side to side and up and down and around, but they're not spinning anywhere. They're just vibrating. And the force between them is moving. So the little force bits that are trapped between the electrons are the black ones. I shouldn't have drawn them as red. And essentially, the distance apart they are is essentially a frequency. And so when one of these electrons is banged at a little harder than usual, it might shudder or move out of position a bit, and then the stuff bouncing between it, some of that stuff might escape. And it's going to escape at the frequency of the distance. So that means the bits will have that same frequency. And that frequency will be something like visible light. And so to create, like X-rays, which have a really tight frequency, you can sort of understand that these electrons need to be really close together. Okay, sorry, wrong color. Alright, so for an X-ray to be created, the electrons need to be really close to each other, and then one of the electrons moves out of position a little bit, and some of that force escapes as a couple of blips, and that's an X-ray. But those have to be really compressed electrons that have been forced close to each other to create the X-ray. So that's why the X-rays are rare. It's because you need a lot of pressure to force electrons close enough to produce an X-ray. Or they have to be in the inside of the atom, where they're kind of shielded, and maybe those ones are close enough to produce X-rays. But the external electrons probably have big gaps between each other, and they can produce all kinds of different radiation. Alright, I don't want to really get into radioactive decay, but this is the basic structure of the atom, and you can sort of understand that with certain geometries, where you have triangles, and then you can have octagons and all kinds of different shapes, and you can understand that if these shapes would always end up with sort of weird balances, like a triangle would have 2 things at the bottom and 1 thing at the top, no matter where you kind of put a line through here. And so you can have a disproportion. That is, you can have a difference in the charge. And that's essentially the foundations of magnetism, which is basically just creating a circumstance where you have more have more of the red bits exposed, you know, in a position of you know, showing their butts or whatever, you know, looking this way. The red bits are all kind of looking that way, and the black bits are all looking this way, so to speak, in terms of how they're shaped in the atoms. And because of that, then any kind of radiation that comes in, if it's red, it'll end up reflecting off this, and if it's black coming in here, it'll end up reflecting off that. And you can sort of understand then if I put two magnets that have the same relationship in terms of how they're dealing, how they're polarized, in terms of how their atoms are all geometrically lined up, that you have to have certain special atoms to be able to do this alignment thing. You have to have certain special kinds of atoms where the electrons are on one side and the protons are on the other side predominantly. And so it takes a special kind of geometry to create magnetic material. But once you have that geometry, then you can sort of understand that all of this red force is reflecting and all this black force is reflecting, and therefore you have a great deal of pressure saying move away and move away, and that's why the magnets repel. And then when you invert it, the exact opposite's happening. All the pressure is leaking out. As I pointed out, all the black energy will leak out of the red, all the red energy will leak out of the black. You'll have very low pressure, and the two magnets will be pushed together because this external force is still acting on it constantly. The little bits of force that fill the universe. So it's probably enough as a general. So the point is that magnetism really is everything. It's holding atoms together, is the fact that these are charged particles. Their charge is essentially a representation of their magnetic properties. So the electron and the proton are essentially the magnetic monopoles. They're the cause of what is the polarization, and this force is essentially the trapping of the force between electrons and protons, and the releasing of the force between protons and electrons is the function. So the fact that the force leaks out perpendicularly is essentially the function, and this is perfectly consistent with experiments like when electrons are moving through a conductor, you know, with electricity. The idea is they're being pushed by the force, and some of that force leaks out perpendicularly as it goes into a proton and it comes out perpendicularly, but it doesn't really matter how. The point is it's always, the force is always perpendicular to the movement of the current. So there's always this right angle, and that defines the function of the connection between electricity and magnetism. The connection between electricity and magnetism is strictly and completely dependent on this idea of perpendicular function. One thing is moving in one line, and the force has to interact with it perpendicular to the line of its movement, and vice versa. So that's all perfectly consistent with all the math and theory behind magnetism. Even though conventional physics doesn't have a particle, they call it a virtual photon. They won't commit to its real existence because they don't have a model that would explain why it exists, because unfortunately they turned gravity into bent space, so they can't call it virtual bent space. So they're stuck with no mechanism, when the mechanism is the same that creates gravity. So gravity, magnetism, and the forces holding the electrons and protons together, it's all the same force. It's all the same force bits that are causing the pressure. The universe is just a sea of this pressure created by the little bits moving the speed of light, and it causes the heavier matter bits to move some other speed, something slower than the speed of light. And they're always slower than the speed of light. Yeah, so I think, hopefully that helps. I might be able to do it one step simpler, but but there's no ether. There's no, I didn't get into waves, but there's nothing in the real mechanics that that's waving anything. There's no medium that something flops through or wobbles through or does any of this stuff. There's nothing serpentining its way through the universe. It's all square geometry, straight lines, and it's all made out of the tension created by the force moving between the different bits. So they're all locked in a magnetic position. You can sort of understand it if you think about a bunch of magnets. You take little flat magnets and you put them between two pieces of glass so they can't flip over. And you have them all repulsive, one pole up. They won't be able to go into each other. No matter what you do, you can't force them into each other, and they'll stay in a tension. And if you put some other magnets, in that field, you can create complex geometry as long as they can't flip over and then move into each other. And so those are the forces of tension. That's what's creating all the tension that creates atoms, that ties atoms to each other, locks them into each other, that creates all the material objects. And the force interacts with those atoms on a subnuclear way. It interacts with the electrons and the protons. It hits the electrons and the protons in the atoms and associated with the atoms, and it moves them, and by moving them, the whole atom changes. The whole structure has to change. The tension moves through the atoms then. But on the force level, it's always the speed of light. But obviously the speed of light, you can travel very erratic ways. If you go down the road weaving, bouncing off the curbs, it could take you a long time to get somewhere, even though you're going 50 miles an hour. And the same thing happens to force. Once it gets inside of matter, it can take it a while to get out of the matter. That's why light slows down when it goes through glass or water. It's because it has to go through the force trails. It has to travel between the electrons, and the electrons aren't lined up in a straight line. It has to go a geometry to get from one place to another. Okay, so probably enough. Till next time and such. I don't know what I'll title this because it's just another type of overview, but I guess I'll call it something. I'll think about what to call it, and then I'll call it that, I suppose. So, till next time.